So ionic radius we have seen, and we have also discussed why cations are smaller than the neutral atom and the anions are bigger than the neutral atom. It is because of that loss of one electron, the nucleus is effectively attracting the electrons towards itself, and hence the cations are found to be smaller than the corresponding neutral atom, and the anions are found to be bigger than the corresponding neutral atom. Now we are going to see the ionic radii of isoelectronic ions. Isoelectronic ions means the ions containing the same number of electrons. Look here in the first column I have put ions. In the second column I have put the number of electrons present in the ion, and in the third column I have put the nuclear charge, and in the fourth column I have put the radius of the ion, which is given in terms of Armstrong unit. Look here, N3 minus, that is in nitrogen, 3 electrons are taken off. Sorry, 3 electrons are added, 3 minus. Nitrogen atomic number is 7. So it contains 7 protons and 7 electrons. As the charge is now 3 minus, 3 more electrons are added. Therefore, the number of electrons becomes 10. So now it is with the 10 electrons and the nuclear charge plus 7, and the radius is 1.71. Oxygen atomic number 8. So it's supposed to contain only 8 electrons. In addition to that, I have put 2 electrons to make it O2 minus. So this ion also contains a 10 electron, nuclear charge 8. See, the radius has come down to 1.40. Look here, in both the cases, the number of electrons only 10. But here, the radius has come down from 1.71 to 1.40. It is because of that one additional positive charge. So this one charge is more, therefore the electrons are effectively attracted towards the nucleus. Therefore the shrinkage has taken place and the radius of the ion has come down. Look at the fluorine minus. In the case of fluorine minus, the atomic number is 9. Therefore it contains 9 protons and 9 electrons. 1 electron is added so that it becomes an anion with a minus 1 charge. Therefore 10 electrons. See, in the first case 10 electrons are attracted by the 7 protons. In the second case 10 electrons are attracted by the 8 protons. In the third case 10 electron is attracted by the 9 protons. So what happens? There is a decrease in the ionic radius. But look at the radii difference. It is only of the order of 0.3. It is only of the order of 0.1 here. But when you take Na plus, see, the difference is vast, very high. The reason is, in Na plus, proton goes excess. It is found in excess. The number of electron is 10. Already the number of electron is 11. One is removed and you are getting a cation with a unit positive charge. Therefore the 10 electrons, but 11 protons are attracting. Therefore there is a vast difference. Say from 8 to 9, there is a decrease of the order of 0.1 angstrom unit. But in this case, there is a change of the order of 0.4 angstrom unit. Similarly, for the next case, Mg2 plus, there is an order of 0.3 angstrom units. Therefore, the ionic radii depends upon the number of electron and the nuclear charge. Now, what happens to the ionic radius? Along the period, it decreases. You know the reason, because the nuclear charge increases and the size decreases. And also when you move from left to right in a periodic table, atomic number increases. Atomic number means the number of protons. Therefore, in order to compensate the increase in the positive charge, the more number of electrons are added to the same subshell. So there is no increase in the principal quantum number, but the distance between the outermost cell and the nucleus remains the same. But at the same time, the Coulombic force of attraction increases. Therefore, the size of the atom decreases. While the size of the atom decreases, naturally the size of the ion will also decrease. Similarly, when you come down, the ionic size increases. It is because of the introduction of new orbits. Because when you come down, new principal quantum number is seen. In the case of hydrogen 1s, in the case of lithium 2s, in the case of sodium 3s, potassium 4s, rubidium 4s, 5s, something like that. But you should carefully look here. You take the size of the lithium plus ion, take the size of the sodium plus ion. If you look at the difference in the size, it is an appreciable size difference. If you take a sodium plus ion or potassium plus ion, there is an appreciable size difference. But if you take potassium and rubidium or rubidium and cesium, the increase in the size is not significant. It is because of the introduction of the 3D series in between potassium and rubidium and the 4D series in between rubidium and cesium. And due to the presence of the transition series in between, the electrons are added to the same subshell. Therefore, that entire increase in the D atom decrease in the size in between in the transition is compensating the increase when you move down. Therefore, the increase happened when you move down and the decrease happened in the transition metals. They compensate each other, and hence the size difference found between potassium and rubidium or rubidium and cesium are not very significant. So this particular point you should understand. They are not very significant. And the next one, this is another very interesting thing, ionization energy. It is also called ionization potential. It is the minimum energy required to remove an electron from the outermost orbit of an isolated atom in its ground state electronic configuration. Every word in this definition is very important. So look at the first word. It is the minimum energy, which means that I am intended to remove one electron from an atom. Suppose if I give some 10 kilojoule of energy, I can just remove one electron. If I give 20 kilojoule of energy, the same electron will come out much easily. If I give 30 kilojoule energy, much easily. Therefore, I should not say it is the energy required. I should mention the word minimum. It is the minimum energy required to remove. So try to understand the importance of the word minimum. So what is the minimum energy which is just sufficient to remove one electron? That one is very important. Because if you give a little more energy, another electron may also go out. But ionization energy, one electron. And that electron should be removed only from the outermost orbit. You should not remove the electron from the inner shells. It is possible. It is possible to remove the inner electrons. But the electron should be removed from the outermost orbit. And moreover, the atom should be an isolated atom. Why it is an isolated atom? If the atom is found together along with other atoms, the electrons are subjected to the attractive force of other nuclei also. In such a situation, the outermost electron will be attracted by several nuclei. Therefore, your energy spent to remove the electron may not be accurate. Therefore, it should be done with the isolated atom. And finally, it should be in the ground state electronic configuration. because if the atom is in the excited electronic configuration, the electronic distribution will be different in the excited state. In such a condition, you should not measure the ionization potential. Therefore, every word that is mentioned in the definition is very important. So, the ionization energy is the minimum energy required to remove an electron or one electron from the outermost orbit of an isolated atom in its ground state electronic configuration. Now, I am taking an atom, I am removing one electron, and I'm getting an ion with a unit positive charge. This ionization energy is called first ionization energy. If I try to remove one more electron, that unit positive ion now become dipositive, two positive charged ion. On the removal of one more electron, what is the energy spent here to remove this electron from an ion with a unit positive charge? This is called the second ionization energy. If the process is extended and I am trying to remove one more electron from a 2 plus charged ion to make a 3 plus charged ion, what is the energy spent to remove this electron? It is called third ionization energy. Normally, third ionization energy is the greatest, and the second ionization energy is lower than the third ionization energy, and the first ionization energy is the least among these three ionization potentials. The reason you may be knowing, in the neutral atom, the electrons are attracted by the nucleus. In the unit positive charge, the nucleus power is a little bit extra because it has already lost one electron. Suppose if 10 protons and 10 electrons are present, in the second case, it is 10 protons and 9 electrons. The 9 electrons are effectively attracted by the 10 protons. So the energy to be spent to remove one electron among the 9 is a little more. When one more electron is spent, now the nucleus is containing 10 protons, but the outer shell contains only 8 electrons. So now 10 protons are attracting 8 electrons, and hence the removal of one of the electrons of the 8 will become much more difficult. So that is why the third ionization potential, the second ionization potential, first ionization potential, this is the decreasing order of energy. The ionization potential is expressed in the unit electron volt or joule. And for your convenience, I have put the conversion factor over here. 1 electron volt is equal to 1.602 into 10 power minus 22 kilojoule. The ionization potential can be measured either per atom or per mole of atoms. So ionization energy or ionization potential is the minimum energy required to remove one electron from the outermost orbit of an isolated atom in its ground state electronic configuration. Any number of electrons can be removed. The ionization energy spent for the removal of the first electron is called first ionization energy, and the second electron is called second ionization energy, and the third electron is called third ionization energy. When you compare these ionization energies, the third ionization energy is of the highest value, and next to that, second ionization energy with a little bit lesser value, and the least among the three is the first ionization energy. And the ionization energy is expressed in the units of electron volt or joule. And 1 electron volt is 1.602 into 10 power 20 minus 22 kilojoule. And the ionization energy can be measured per atom or per mole. Now look here, look at this table. This table is a very important table giving a lot of information. Here, the numerical value that is given next to the symbol of the element is the ionization potential in electron volt per mole. If you remove the electron from 1 mole of the substance, then this much electron volt energy has to be spent. You need not refer both the values. This is per atom, this is per mole. That's all. That is the difference. So this is, sorry, value within the bracket. Sorry, this is expressed in electron volt per atom. The first value is electron volt per atom. This is electron volt per atom. This is kilojoule per mole. Don't get confused. The first value is kilojoule per mole. The second value is electron volt per atom. Let us take any one of them. The first value, let us say the first value, which is kilojoule per mole. Look at the hydrogen ionization potential, 1312 kilojoule per mole. Look at lithium, it is 520 kilojoule per mole. Look at sodium, it is again less. Look at potassium, it is further less. Look at rubidium, again it is less. Look at cesium, it is less. So when you move down the group, the ionization potential decreases. Why the ionization potential decreases? When you move down the group, the size of the atom increases. You take any group. See here 899, 737, 589, 549, 502. Here see 800, 577, 579, 558 and 589. There is a small increase here. These are all anomalous behavior. And also see here also. It is 1086, 786, 760, 708 and again there is a small rise. Small increase. So look here. So when you move down the group, the size increases. So when the size increases, the outermost electrons go far away from the nucleus. Even though the nuclear charge is also increasing, they go far away from the nucleus. Therefore, the outermost electron can be easily removed by the expenditure of a very small energy. That is why when you move down the group, the ionization energy increases. Now look here, when you move along the period, a size decreases. You know the reason for the decrease in the size. And as the size decreases, the outermost electron comes closer to the nucleus. Therefore, more energy has to be spent to remove the electron. But look, this is 520, 899, 800. There is a decrease here. And then 1086, then 1402, then 1300. See, a small variation here. So nitrogen ionization potential is greater than carbon. It's all right. But oxygen supposed to be much greater than nitrogen because the size is small. But if you look at the ionization potential, nitrogen has the higher ionization energy than oxygen. And then fluorine the highest. And then the neon even much higher than the fluorine. Because neon is an inert gas which will not be ready to lose an electron. But fluorine is always having an attraction towards electron. It is not ready to lose the electron. So along the period, in general, ionization potential increases as the size decreases. When the Y size decreases, along the period, atomic number increases. In order to compensate the increase in the positive charge, electron is added to the same subshell. Therefore, the distance between the nucleus and the outermost shell is not changing, but at the same time, the nuclear charge and the number of electrons increase, which increases the Coulombic force of attraction. Therefore, the size of the atom decreases. The decrease in the size of the atom brings the outermost orbit closer to the nucleus. Therefore, the outermost electrons are effectively attracted by the nucleus. Hence, more amount of energy has to be spent to remove the electron. And that is why the ionization potential increases along the period. But down the group, the atomic size increases. But the increase in the nuclear charge is not appreciable when you compare with the increase of the size down the group. Hence, the outermost electron can be easily removed. That is why the ionization potential decreases down the group. Now look here. So what are all the various factors influencing or affecting the ionization energy? The first factor which affects the ionization energy is atomic size. That is what I have discussed just now. It is because of the Coulomb's law or Coulombic force of attraction between oppositely charged particles. So atomic size, when the size is big, the outermost electron is far away from the nucleus and it feels less attraction because of the distance. And hence the electron can be easily removed in the case of big atoms, and the removal of electron becomes difficult in the case of smaller atoms. And the second factor is the nuclear charge. If the nuclear charge is higher, it effectively attracts the electron. Therefore, the second reason is, or the second factor determining the ionization energy is the nuclear charge. Third one, the number of electrons in the inner shell, which we call shielding effect or screening effect. If more number of electrons are found in the inner cells, the attraction that is spread by the nucleus will be screened by the inner electrons, and the electrons present at the back of the inner orbitals will get shielded, or they are getting protected from the attractive force of the nucleus. Hence, they can be easily removed. And the fourth factor is a penetrating effect. Penetrating effect means this is the penetration of the orbital in the nucleus. See, s orbital is very close to the nucleus, which has the more penetrating power. So this penetration effect is discussed for orbitals with the same principal quantum number. You should never compare the 1s and 2p or 3d or 4f. Everything should be compared with the same principal number. Say, for example, if I take 4s, 4p, 4d, and 4f, everything should be of the same principal orbit, same orbit. So if you take a 4s, a 4p, 4d, and a 4f, then 4s is found to be more penetrating than p. P is more penetrating than d, and D is more penetrating than F. So, because of the penetrating power or the penetrating effect, ionization energy to remove, which is used to remove the electron from the s orbital, is the highest, and then in the decreasing order it becomes P, and then D, and finally F. So this is the decreasing order of ionization energy pertaining to orbitals with the same principal quantum number. And the fifth factor is electronic arrangement. Look here, this is the important idea. The ionization energy is high when the electronic configuration is completely filled. Similarly, when it is half filled. Because the completely filled electronic configuration and a half filled electronic configuration, they are all stable. No system will try to go from stable configuration to an unstable configuration. So completely filled configuration is stable. So when you try to remove an electron from the completely filled configuration, you are moving from stable configuration to an unstable configuration. which will not allow. Similarly, half-filled configuration is stable. So when you remove an electron from the half-filled electronic configuration, you are trying to move from a stable configuration to an unstable configuration. Suppose if you take oxygen, oxygen is partially filled with the P4, the p orbital containing 4. So partially filled is unstable. But if you remove one electron, it becomes a P3, which is a half-filled electronic configuration. So in such cases, the electron can be easily removed because the removal is favoring the stability. But in the case of nitrogen, it is half-filled with the P3 electronic configuration. So removal of one electron will lead to P2 configuration, which is partially filled, which is unstable. That is why when you are comparing the ionization energies of nitrogen and oxygen, even though nitrogen is bigger than oxygen, oxygen supposed to be of high ionization energy than nitrogen. Nitrogen is found to be with a high ionization potential than oxygen because oxygen can readily lose the electron to attain the stable configuration of a half-filled level, whereas nitrogen is already stable with a half-filled electronic configuration, which will not be ready to lose the electron to become a partially filled electronic configuration, which is unstable. So if the loss of electron leads to a stable electronic configuration, that system will have minimum ionization energy. If the loss of electron leads to an unstable electronic configuration, then that system will have the maximum ionization energy. That is why noble gases have very high ionization energies. So these are all the various factors determining the ionization energies. Now look here, somebody has unmuted. Please check. All of you, please check whether your microphones are muted. Now look at this graph. So ionization energy, when you move from left to right in the periodic table, that is along the period, it increases. Down the group, it decreases. The reason, you can discuss the reason in terms of all the 5 factors which I have explained earlier. But if you closely look at the change of first ionization energy with the atomic number, for hydrogen, it is here because it has 1s1 electron. For helium, there is a sudden change, much high. The reason is 1s2 is a completely filled electronic configuration. So if you remove one electron from this, it goes to an incomplete electronic configuration. So the completely filled electronic configuration is stable. So because of the stability of the helium, it is very difficult to remove this one electron. At the same time, when you move to the atomic number 3 with the lithium, lithium has 1s2, 2s1. So lithium has a partially filled electronic configuration. If this one electron is lost, that lithium plus will be found with a completely filled electronic configuration, which is stable. So from unstable condition to stable condition, therefore the ionization potential falls down rapidly. So when you go to beryllium, again there is a small rise. When you go to boron, again it decreases because boron has 2s2, 2p1 electronic configuration. This 2p1 is unstable. So if you remove this, 2s2 will become a completed electronic configuration. Then carbon, no problem, usual change because of the size. And nitrogen, it goes still higher because of the half-filled electronic configuration, stable electronic configuration. But there is a fall when you go to oxygen because it is a P4, partially filled. After losing one electron, that becomes half-filled. And then fluorine, it increases. And then neon, almost equal to helium because neon is also a completed electronic configuration with a completed octet, whereas helium is with a completed duplet. Both are noble gases. Therefore, both are having almost equal ionization potential, whereas all other things, there is a variation. But in general, when atomic number increases, the first ionization potential is supposed to increase. So the increase is not a gradual, but the increase is having a small variations because of the other factors like the electronic configuration. So when you move down the group, there is increase in the nuclear charge, there is increase in the atomic size because of the introduction of new energy levels, but increase in the number of inner electrons is also there. Therefore, the combined effect of all these three things will result in one thing, that the ionization energy decreases down the group. So that is the thing. It decreases down the group. So with this, I think I have shared everything pertaining to ionization potential. Now you try to rejoin. I'm going to cut off in the meeting. Try to rejoin immediately.